Okay, so, you know, the lead-in is the picture here. Same spill, same oil, very different behavior, right? So it makes a difference if you're going to plan a response. It's good to understand some of the processes that's going on. So this is a new slide I added in because, you know, our group in Seattle, we've been kind of looking at this issue for a while. And if you're a responder, you need to look at this and understand what happened here, because you guys are getting, you know, Bakken coming in on the trains also. And we just had a spill of this stuff in the Mississippi River off a barge. And we were very careful not to let that happen. Okay. All right, so, you know, I'm not going to spend time on repeating stuff that Jordan went over, but there's the picture. This is a good summary picture of what's going to happen to the oil when it spills into the water. So this is kind of like what Jordan showed, right? This is from our adios model. And you can see that it's different oil types, different persistence. So I always tell people, you know, oil doesn't last forever. I mean, Jordan made that point, and I'll make it again because it's important to understand that, you know, nature takes care of it. Sometimes it takes a long time to go away. Sometimes it doesn't. But it's important to know what it is, what's going to happen to it. Okay, so let's look at evaporation again, just from a little different light. So here is a field, here's a field experiment that was done last year by these guys. It's actually funded by Kinder Morgan, and this is looking at the oil bed. I don't know if you've heard about the oil that's coming out of Canada. Yeah, this is a Keystone pipeline oil, right? So they mine it. The thing comes out, it's bitumen, so it's like tar. So they actually scrape it off the ground, and then they mix it, they dilute it with, you know, something like a gasoline, diesel type product, so it liquefies, and then they can pump it into a pipe or, you know, fill up a barge or something. So they did a study here, and yeah, okay. So these are just different states of turbulence. So here's, they just put it in a pond here, let it sit, a little mixing and a little more mixing. And what you can see over time, the density increases, right? Here's water. So this, once again, this reiterates what Jordan says, that the oil spills, evaporation happens, the density changes. Okay, so, you know, this is important. It changes. That changes the behavior of the oil. It could change your response options. And, you know, this is water. Seawater is over here. With this oil, if you're familiar with it, the question is, will it sink, will it float? So I have the report. I have a copy of the report this came out of. It's on my computer. I have this report. I have a report that Environment Canada did on this oil. And I have a report that we got grad students at the University of Washington to do. So if people want that, just come see me.
Some of those reports are on the CD.
Okay.
Because I sent those to Randy and he put them on the CD.
Okay. So if you got them, you got them. If you don't, you can come see me and I can get them to you. So it's very interesting. Okay, so here's the question. First quiz question. All right, so you got oil. You got oil like that. You got a heavy fuel oil. It sits in the water. The light ends evaporate out. Is that oil ever going to sink? So how many people think that the oil could start as a floater, the light ends evaporate, and that oil could sink? Show of hands. How many people think that's possible? Okay. Most people think it is. And you know, for the most part, I think if you would ask people, they'll agree that it can probably happen. We haven't seen that happen in 30 years doing response. You know, from our experience says that it starts as a floater, it remains as a floater. You know, most of our experience comes in salt water. So the question is, why is that? So here's the deal, right? So the light ends evaporate from the surface of the oil. You got oil drops. So for the oil to evaporate, it's got to get to here. So right off in the beginning, right, a lot of the light ends evaporate. But then the other stuff that's mixed in here, the light ends, they have to get to the surface of the oil. And as the oil evaporates off, as Jordan pointed out, the viscosity increases very quickly, which means it makes it very difficult for the small molecules to diffuse out to the surface of the oil. And what you see is like in this picture here, you know, you can't get all the light ends out because it's just too difficult for the molecules to diffuse to the surface. So they call this diffusion limited evaporation. So, you know, it's a rare occasion where you see oil started as a floater and it actually sinks. I wouldn't say never, but it's rare. And I think in salt water it's almost impossible. It's going to look like this. All right, so here's another one. This is from the Environment Canada study. This is a cool picture. So what they did here was they had oil. They had this dilbit oil, and they had one set they just left it in the dark for several days, and another one where they actually exposed it to light. This is the one exposed to light, and what you see here is that it had a crust, and you know this crust will also prevent stuff from diffusing to the surface. And I think, you know, this might be a mechanism for tarball that you see with the crust in the outside. You break it open, and you can still smell the oil. My guess is that if that oil was in the dark all the time, it probably wouldn't be that way. So, you know, this is another mechanism for what happens to the oil. Okay, same picture. Dispersion. I think Jordan covered dispersion. Once again, the audio's output, and the deal here is that the winds are different. 15 knots, 20 knots, same oil, same mono-oil, and you can see here, more turbulence, more oil in the water column. It's just like that spill that Jordan put up, where all that diesel got into the water column. Here, stronger winds, less time. So, once again, physical processes, keep that in mind. It makes a big difference. Here's a real, this example this year was, to me, was surprising. So this is a boat that's grounded off of the entrance to Guam, Apra Harbor, right? It had 10,000 gallons of diesel, and by the time they got out to this thing, they determined half of the oil was gone, but nobody saw any kind of a sheen, and nobody reported really smelling oil. So the question is, well, where did that oil go? Nothing on the beach. And you know, this is like, what, maybe 100 yards from the beach? So, you know, the deal is that the oil got in the surf zone, and it just mixed into the water column. But there was no documented kill. Nobody saw dead fish. Nobody saw dead coral. No, the coral got damaged because the boat came across the reef. Jordan's got a cool picture on his laptop of the boat inside of the surf zone, stuck in the reef. So there's another extreme example of dispersion of a light oil. You know, if it's a number 6 oil, I guarantee you they would have got some oil on the beach. Cool picture.
Excuse me.
Yes?
So it didn't kill any sea life because it was just dispersed?
I think, you know, we talked about this in the office, and I think there are two things. I think it dispersed quickly, so the concentrations were low. But the other reason is because the exposure times are short. Because remember, if you're going to kill something, it's a matter of how much you're exposed, you know, how much you expose it to it and for how long. So in this case, it's dispersed dispersed quickly, and it's really high energy. So that polluted water moves through quickly. So they never saw any dead critters. You know, there was another, years ago, there was another bigger fish processor that got grounded on an atoll in the Pacific. And that had a couple of 100,000 gallons of diesel, and there was dead coral, you know, in the vicinity of the vessel. Spreading, Jordan covered this. This is a cool picture. He didn't have this cool picture. This is what the oil spill looked like on Saturday in Galveston. So this is the 380. So it's a very viscous oil that was spilled. So for me, the spreading deal is that it happens quickly, it happens early in the spill, and then other forces take over. Winds and currents take over. So it's not a big deal after the first few hours. This picture I took off the Arizona. Good example of that spreading. Okay, so these are the things that are near and dear to me. Winds and currents, right? That's what I made my living doing for short and forever. So this is what controls everybody else has. Yeah, currents going to take things down current. What a lot of people don't realize is that the winds are very important. In fact, I guarantee you, if the winds are not blowing onshore, that oil is not going to come up to the beach. All right, so you need winds blowing onshore to get oil on the beach. The currents will not bring the oil onto the beach. You could bring the oil close to the beach, but it's not going to take it off. Because if you think about it, if the currents are running into the beach, the water's going to pile up, and you're going to flood the beach. Right? It's not going to happen. If the currents are running off the beach, then the water will all run away. We're not talking about tsunamis. That's a different story. But normal currents, at some point, they'll always run parallel to the beach. It could be close to the beach. So you need onshore winds. So if you hear of an oil spill, you want to say, man, is it going to get on the beach or not? First thing we look at are the winds. Which direction are the winds blowing? If they're blowing onshore, you might have a problem. If they're not, then you've got a longer time window. So these are the kind of things we do. This one, this guy moved at about 7% downwind. So if the winds are moving at 10 knots, then this guy's going to go downwind at 7% of that. Oil, fresh oil is about 3%. So that's another rule of thumb. So you currents and you add 3% to wind. So here's another one that we dealt with recently, right? The tsunami debris from Japan. This is a crazy YouTube video. But this thing here is a dock that got washed off in Japan. One of these ended up in Oregon, one ended up on the coast of Washington. These things last forever. It's concrete, and in the middle it's styrofoam. So that stuff is it's going to last forever. But this one was right off of Hawaii. This guy was a fisherman. They caught all the fish they could. Then he hopped on, did a YouTube video, and then he called the Coast Guard and said that they have this thing floating out there. It didn't come ashore. It's somewhere out in the North Pacific. But the winds, once again, the winds played a big part in whether this thing actually came ashore or not. Okay. So, quiz questions. Okay, so fresh oil, 3% of the wind. Right, that's the rule of thumb. Is that going to change for oil over time? So how many people think that that's going to change over time as the oil weathers? You heard George's talk this morning. Okay. So why do you think it's going to change? Right. So did you hear that? So as the density of the oil changes, the oil will sink, will float lower in the water, and less of a effect of the winds. So that's something to keep in mind. Whereas, you know, the whale in the dock, the whale's going to stay that way until something eats it. The dock will stay that way forever. Slicks, elongate direction of the wind. You know, you never see a circular slick in the ocean very long. So, does anybody want to take a guess why that is?
So oil on the outside is more affected by the wind than oil in the center. It has that surface area that's being pushed, especially.
No, not quite. So here's what we think is happening, is that the winds, you have waves, and as Jordan said, you get dispersion in the vertical, so you get oil droplets. Now when the oil droplets go subsurface, they don't feel the winds. So they lag behind. All that remains on the surface will continue to move at 3%. So you get this thing elongated, and then, you know, those droplets come back up. So the droplets go down under, they go slower with the wind, they fall behind, they come back up. So now you get this thing stretched out in the direction of the wind. That's our story. So here's another one. Rule of thumb, 90% of the oil is in this is wrong. 90% of the oil is 10% slick area. So once again, it has to do with the winds working on the oil. So the oil gets pushed by the winds. So you never see an even distribution of the oil on the surface. You know, this was brought out this morning that, you know, you can see a footprint from the satellite, but you can't tell how thick it is. One of the questions we always ask the people going out to look at the oil is, you know, what did it look like? What's the percent coverage? They'll say, well, you know, 50% sheen, 20%, you know, open water or something like that. So it's never uniform. The Coast Guard folks, they always like to estimate the amount of oil based on what you see on an overflight. That is really, really difficult to do. We discourage people from doing that because it is just not uniform, both in distribution and in thickness. If you got to do that, I would suggest you give a range. We have, you know, the overflight thing here, and the one online will give you a rule of thumb, and you can get ranges. That's the way to do it. So here's a cool picture, wind effect, and anytime there's some kind of wind, you'll see that. You'll see this type of setup, whether it's here or out in the ocean or on a lake. You'll see these windrows set up, and this is the theory here. This is the circulation that it sets up. And so these areas here are collection areas, right? You can see this. This is a diesel spill off San Diego. So the winds are blowing this direction. So my guess is that, you know, the vessel that leaked the oil probably is going this way, and the winds are blowing this way. It's a real common thing to see. And this kind of stuff will also help mix the oil vertically in the water column. So these are called Langmuir cells. And if you just look at open water during wind, you know, moderate wind, high winds, you'll see that. Okay, different type of currents. Tidal currents, you know, it's back and forth. No net. Unless you're looking at where's the oil going to be in 2-3 hours. You know, then tidal current is important. But if you're looking at 2-3 days, you know, we don't bother with tidal currents because it goes, it comes. These are more interesting, right? These are coastal currents, surface coastal currents. These are actually measured by HF radar. I don't know if you've heard of HF radar, CODAR. So there, you know, California has almost the whole coast measures this, and you can get this online. It's almost real time. It's you know, it's within the last hour. These currents off of California are primarily controlled by the winds, because you don't have any large rivers here. Okay, then you get to open ocean currents. And this is what it is. Out in the ocean is just a series of eddies. So you know those guys looking for that airplane in the Indian Ocean, even if they find pieces of the plane floating around, it's going to be very difficult to try and backtrack that when the plane crashed. Because reality is that the deep ocean looks like this. So it's just a series of eddies. It's like the winds, right? You know, it's like this. You've got the big circulation, but inside of that you have just a series of eddies. Convergence zones. These are important because obviously this is where you want to skip. So how do you get these? What do they set up? Why do they set up? Okay, here's an example. Right, so this is the feature. And this is the MODIS image from the day before. So, you know, what you see here is large rain event. Flush stuff out. And this will create an interface between the fresh water and the salt water. And that'll allow for these type of collection areas. So that's where the oil collects. That's where all the rapid birds will collect too. The biggest bird kills in the Exxon Valdez didn't happen in Prince William Sound. They happened way downstream when you had these convergence areas. The oil came together with the birds. That was just bad news for the birds. A different type of convergence. So I saw this on Google Earth. Whoa, this is really cool. And then this is the spill, right? This is the spill off of Humboldt. So going around and you collect it in these type of features. So I think these features are a function of the bathymetry, and you can get some pretty good currents that interact with the bathymetry. I'm not really sure, but that's my guess. But you know, obviously this is where the oil's going to line up. So that's where you look for it to go collect it. Okay, so forcing functions come in all different scales: small scale eddies, large scale currents, small scale stuff like Jordan pointed out. You know, like the vertical dispersion, it'll affect the appearance distribution, the initial spread. Larger scale stuff will affect the advection, how the stuff's going to move over a longer time period. Okay, quiz question. Will the amount of oil make a difference as to where the oil's going to go? So how many people think it's going to make a difference if I lose 100 gallons or 10,000 gallons of oil? Okay, so here's the deal. Right, so initially, what's going to happen is it's going to spread over a larger area if you got more oil. What it's going to see is it's going to feel the same winds and the same currents, right? That's going to be the same. So the answer is that in the initial first few hours, it's going to make a difference. But once you get out for days, weeks, it's not going to matter because it's going to be the winds and the currents. So really, from where I stand, the difference in the initial spill will make a difference how much oil gets to the end point. But in general, it's going to go to the same place because the winds and currents are going to be the same. Okay, so beach processes. Rip currents, right? If you're down here and you go swimming, you don't want to get caught in one of these. But the oil gets caught on it, it'll pull oil away from the beach. Here's a picture, right? So these are rip currents. So if the oil's in the surf zone, it'll get drawn out this way. Oil on the beach. This is the oil from Texas from yesterday. That's the heavy oil. That's what it looked like on the beach. Buried oil. If you go out to the beach and you watch how the waves come up on the beach, you'll see it picks up sand from the lower part of the beach, carries it up, and drops it on the upper part of the beach. So if the oil gets stranded on the upper part of the beach, it could get buried because then the waves will start to bring sand. So that's something that you're going to look for. And here's a typical example of when you can get on the beach and how you can get stuff buried. So falling tide, so the oil gets stranded on the beach, and an onshore wind. And earlier somebody mentioned the Honey Bay spill, and that one was very interesting because the oil, for a long time, it didn't come on the beach because the tide and the winds were out of sync. When the tide was falling, the winds were blowing offshore. So it just, for a long time, the oil just hung out there. That was kind of interesting. There's the picture that Jordan showed. And, Jordan mentioned the other way to get oil to sink is to put sand in it. There's an example. And this is another cool one that people are just studying now. So this is biological activity. It takes the oil, does this, and does this. So we heard a presentation last week,
Right.
and the guy estimated that about 3% of the Deepwater Horizon oil ended up on the bottom through this marine snow option. Okay, real quick, go through this. What do I think happened here? So first clue, right? Bakken oil, high API. That means it's not very dense. It's got a lot of light in it. So the train derailed. At least one tank was whole. And then key point, there was an ignition source, somehow sparked or something. So that oil started to burn. And then the nearby tanks heated up. These tanks are not vetted, so they heat up, the pressure builds in the tank, and then the tank blows up. So you get this rain of gas and oil that catches on fire. And you get this mushroom cloud of burning, rain out of gas and oil. And, that's just bad news. Okay. Last slide. Last point here, right? You heard this already. Jordan's the guy. So let me just say, I got the reports online that I mentioned. I have one here that summarizes biodegradation, which we didn't talk about today. But this is where the buggies eat the oil, the bacteria eat the oil. That's another way oil can go away. So this is a real good summary report that we had, microbiologists at the University of Washington for. So I'll just leave it here. I've got electronic copies of these too. Somebody wants copies, just come see me. Okay, done. Questions? Okay.